A Python CAPTCHA queue isn't just about cramming more tasks through in parallel. It's actually about keeping your automation workflows predictable, completely monitored, and totally safe under heavy load. That is what we're talking about today.
Welcome to this explainer. If you're a developer or DevOps engineer looking to really nail down system design for automation, you are exactly where you need to be. We're going to breeze through the Python automation bottleneck, look at queues as reliability systems, walk through a design blueprint, tackle monitoring and backpressure, point out some common mistakes, and finish up with some critical configuration FAQs. Let's get right into it. All right, Section 1, the Python automation bottleneck, moving beyond simple parallelism. So almost every technical team starts with this exact same simple bottleneck. Basically, one part of your workflow is just sitting there waiting on CAPTCHA-related tasks. The rest of your system, it's completely ready to go, but everything stalls out waiting for these tasks to be submitted, polled, completed, retried, or failed before anything else can happen. At first glance, the solution feels pretty obvious, right? Just add parallelism, use threading, use asynchrono, submit a bunch of tasks all at once, and pull multiple results so you can just move faster. And honestly, that naive brute force approach actually kind of works for small batches. But as soon as that workflow becomes a part of real, day-to-day operations, the whole question changes. It's no longer just, hey, can Python run more of these in parallel? The real question you gotta ask is, can our team operate this queue predictably under load? Avoiding those nasty rate limit problems, stuck tasks, random cost spikes, and silent failures. That becomes the true goal here.
Moving on to Section 2, queues as reliability systems and protecting the downstream. A proper queue architecture decides exactly how work enters your system, what has to wait, and what ultimately fails. This requires a pretty major paradigm shift. Like the source material says, a CAPTCHA-solving queue is not just a Python implementation detail. It is a workflow reliability system. Seriously, let that sink in for a second. It's not just a script, it is the guardrail for your entire workflow.
Okay, Section 3, the queue design blueprint, your steps to predictable automation. Let's walk through the exact steps to get this set up. I absolutely love a good practical checklist, so let's jump in.
Step 1. Define the workflow role. Ask yourself what business process actually depends on this queue. Is it QA automation, client-authorized research, testing, internal tools? The design has to match how important the workflow is. Step 2. Choose threading or Asyncio I/O intentionally. And Step 3. Set your concurrency limits. Remember, throwing more workers at a problem does not always equal better throughput. Too many concurrent tasks will literally just slam into provider limits and spike your error rates. Let's dive a bit deeper into that architectural choice. Threading works incredibly well when you're trying to integrate into existing synchronous code. But asyncio, that's usually your better bet for new I/O-heavy systems where a bunch of tasks are basically just sitting around waiting on network responses. The takeaway here, don't just pick the one you're most familiar with. Choose based on your specific workload, your architecture, and your future maintenance needs.
Moving right along through our blueprint. Step 4 is adding backpressure. Step 5, separate out your workload types. Look, a massive batch job and a continuous high-priority workflow need entirely different queue behaviors. So don't force every single task down the exact same path. Some tasks can wait, some need VIP priority, and some need much tighter timeout rules. And finally, Step 6, design your retry rules really carefully. Retries are awesome for weird, transient errors, but retrying permanently unsolvable tasks or tasks with bad parameters, you're just burning time and money at that point.
Which brings us to Section 4, monitoring and backpressure and maintaining queue health. Now we're shifting our focus to the actual mechanics that keep your queue healthy and prevent those catastrophic overflows. The absolute crucial concept here is backpressure. Basically, backpressure stops your queue from growing out of control by deciding if new tasks should wait, get rejected, or get routed somewhere else whenever tasks are arriving faster than they're being completed. Without it, your queue just grows indefinitely until something breaks. So bounded queues, load shedding, and adaptive concurrency, those are your essential protections.
And to execute all this at an enterprise grade, you can lean on some specific infrastructure integrations. NATS messaging is fantastic for lightweight task distribution. RabbitMQ gives you those durable queues and dead letter routing. And Grafana, that is basically essential for monitoring your latency and queue depth. These integrations build right on top of your foundations to give you massive processing power, but with total visibility.
Let's look at a super practical troubleshooting matrix straight from the source material. Okay, symptom 1, your queue is growing. The cause, your workers are probably overwhelming the API. The fix, reduce your max workers. Symptom 2, you're hitting an API concurrency limit. Maybe seeing something like error, no slot available. The fix is simple, add a delay. Are tasks just getting stuck? A worker thread probably died on you, so wrap it in a try/except block. And if your memory keeps growing, your results just aren't being consumed. Call get results periodically. It's an absolutely fantastic cheat sheet to keep in your back pocket.
To wrap up our blueprint, Step 7, monitor queue health, and Step 8, assign ownership. Look, a queue without monitoring is literally a black box. Your workflow could be falling miles behind long before anyone even notices. And who owns this thing? Who's keeping an eye on provider limits? Who owns the retry policy? Because without clear human ownership over the configuration, your system's reliability is entirely by accident.
Section 5, common implementation mistakes and the anti-patterns to avoid. Let's run through the things you absolutely want to stay away from. I'm going to run through these fast, so stay with me here. Mistake 1, assuming more workers always equals better performance. 2, having zero backpressure. 3, allowing silent worker failures. 4, treating rate limit errors like they're just normal failures. 5, doing endless retries on bad tasks. 6, tracking only your completion output instead of crucial things like queue depth, failure reasons, and wait time. And finally, mistake 7, building out these automated workflows without actually reviewing platform permissions, rules, and your operational risk. These mistakes are fatal, yet they are incredibly common. All right, finally, Section 6, critical configuration FAQs for fine-tuning your system. Let's tackle a couple of the most common developer questions we see when it comes to scaling this stuff. 10. 10 is the magic number. The recommended number of concurrent workers to start with is always 10. You want to start conservatively. From there, you can adjust and increase, but only after you've monitored your success rates, your average solve times, and your specific provider limits. Next big question, how exactly do I handle API rate limits without completely breaking the queue? Well, the best approach is using a semaphore for asynchronio or a bounded queue if you're using threading. And this is crucial. You absolutely must add short delays between your submissions whenever you start hitting those limits. We're going to end on this thought right here. If your CAPTCHA queue failed silently right now, how long would it take for your downstream workflows to completely break? It's a provocative question for sure, but it is exactly what you need to be pondering to make sure your infrastructure is actually resilient. Thank you so much for joining me for this explainer. I really hope it gave you exactly what you need to go out there and build better, more reliable systems. Catch you next time.